Welcome. This is the lecture for Chapter 12 on uncertainty. I'm going to start showing you things. And a couple minutes in, you're going to be thinking, he's reading the lecture notes from the wrong chapter. I'm not. All shall become apparent. When I looked through, this is a great textbook. Boy, it's a great textbook. There's also, if you're interested, a graduate level version. In the econ community, we call that one Varian, the author, and we refer to this one as Baby Varian, just so you know. Okay, I read through, it's a great book. Read through this chapter and I thought, that seems kind of hard. And I know the material already, and I know it isn't that hard. So I'm going to show you sort of a trick, essentially, that will make it, hopefully, I hope you all go, oh, that's all it is. All right. Let's see if I can make a whiteboard appear. No, don't think I can. Okay. Here's what I'm going to do. Let's say that you want to predict what combination of two things a person will buy. How do you do that? Well, you could do it like this. This is thing one. We'll call it A. Actually, that's not going to work right there. Let me move it around a bit. Here we go. And the pen doesn't work. What am I doing wrong? Pen. Ah. Joy, joy, joy. All right. Now let's try this one more time. All right. This, and the pen's not working again. On the horizontal axis is the quantity of thing A that the person decides to have. On the vertical axis is the quantity of thing B. Now, to figure out what this person will choose, what combination of A and B, we need to know basically two things. We need to know the rate at which this person can trade off A and B. And we need to know the rate at which this person is willing to trade off A and B. What's possible versus what is preferred. Let's say there is what we've called so far a budget line. You know what? I'm going to have to use the mouse because the pen isn't working. The drawings will be a bit sloppy. Please forgive me. There's a budget line. The slope of this budget line is the ratio at which a person can exchange B for A. If you want, let's say you start out right there. and you're not happy with that combination of A and B. You want less B, you want more A. All right, well, rise over run. If you give up this much B, you can get that much A in return. It's the slope of the line. So that's the rate at which you can exchange A for B. Now this is going to be really ugly because I'm doing it with a mouse, not a pen. Here's an indifference curve. All of these combinations of A and B make you equally happy. The slope of the indifference curve at any given point represents the rate at which you are willing to exchange A and B. Down here, you're willing to give up a whole bunch of A to get a tiny little extra amount of B. Up here, you're willing to give up a whole bunch of B to get just a little more A. At this point, the slope of the budget line and the slope of the indifference curves are the same. So the rate at which you can exchange A and B is the same as the rate at which you're willing to exchange them. And that is the consumption bundle you'll choose, because that gets you to the highest indifference curve. To find that bundle, you need to find the point, or points, plural, where the slope of the budget line is the same, is equal to the slope of the indifference curve. So you find a formula that describes the slope of the budget line, one that describes the slope of the indifference curve, set them equal to each other. And that will give you this point. However, it will give you other points as well, because, and again, this is going to be ugly, but okay, here's a lower indifference curve. Well, at roughly that point, the slope of that lower indifference curve is also the same as the slope of the budget line. And yet you know you're not going to pick that because that's inside the budget constraint. You'd be leaving money on the table. By moving this way, more of A and more of B, well, you can have more of both, so you're not going to pick that. What you have here, this line that is tangent to that indifference curve, would give you the consumption bundle you would pick if your income was lower. If, let's say, whoops, your income was like that. Let's assume that they touch. That's a lower, it's the same price ratio of A and B, but your budget line is pulled in. Well, what happens if your budget line was there? Same prices, but you have an intermediate amount of money. Well, then maybe you'd pick, I don't know, that point instead of that point. If you go to the first budget line I drew, you'd be at that point. Well, if you take the budget line and move it in and out from the origin, you'll get a whole bunch of these points, all of which are optimum choices at some income level. This green line moving up to the right is what I learned as the income expansion path. This book calls it the income offer curve. It's all of the optimum bundles at all sorts of incomes. Okay, but you want this particular consumption bundle. You want the consumption bundle that is optimum at that budget line, which I've again drawn badly. So to find that one and not any of the others, you need to do two things. You need to find the point where the budget line and the indifference curve have the same slope, and you need to find the point where the person spends all their money. Now, so what you do is this. Oh, I'm going to try the pen one more time. The slope of the indifference curve is the marginal rate of substitution. I really want this to work. And here we go. The marginal rate of substitution. We want the slope of the indifference curve to be the same as the slope of the budget line. The slope of the budget line is the price ratio. Well, actually, that'd be price of A, price of B. So any combination of A and B that satisfies that will be on the income expansion path. But you also need the person to spend all their money. So the price of A times how much of A they buy, plus the price of B times how much of B they buy, must equal the total income. You plug in stuff, you have two equations and two unknowns. Solve, you can find that point. Okay. Why am I going over again stuff from the previous 3-4 chapters? I'm not. What I just showed you is how people make decisions with uncertainty. Everything I just showed you that you learned from the previous chapters works exactly the same way in this chapter. The reason why when you read through the chapter it seems like new and different material and complicated is only because we've given things different names. I can make the pen work again, pen. What I did draw on the horizontal axis was thing A. Notice, normally I say commodity A, or excuse me, commodity 1, commodity 2, thing 1, thing 2. Here I deliberately didn't call them that. I said A and B. Imagine that you are offered a gamble. I'm going to flip a coin. If it's a fair coin. Comes up heads, you have 10 heads of cabbage. We're not dealing with money. Comes up tails, you have 20 heads of cabbage. All right, maybe you would be there, 10, 20. C1 is how many heads of cabbage you'd have if the coin comes up heads. C2, how many heads of cabbage you'd have if it comes up tails. There's a consumption bundle. These two things are not different commodities in the same world. These are the same commodity, in this case cabbages, in two different worlds. We call it states of the world. In state of the world 1, the coin comes up heads, you only have 10 cabbages. In state of the world 2, the coin comes up the other way, and you have 20 cabbages. Now, once the coin's flipped, you're only going to have one of these, either 10 or 20. You're not going to have both. But before the coin is flipped, you can think of these two possible futures as two different commodities, apples and oranges, Coke and pizza, heads of cabbage if the coin comes up this way, heads of cabbage if the coin comes up that way. I also use C because the book does. Instead of cabbage, just think of it as consumption. You can think of it as money. How much consumption will you have if the gamble turns out this way on the horizontal axis? How much consumption will you have if the gamble turns out that way on the vertical axis? Okay. Now, here's an example. They call this states of nature. Either there's going to be a car accident, we'll call that A, or not a car accident, we'll call that NA. Now, you're going to have some belief, we'll assume your beliefs are accurate for the moment, of the probability of each of these happening. We'll call the probability, your belief, that an accident happens rats. We'll call that pi sub A. And your belief about the probability that an accident does not happen, well, it's going to be 1 minus A, but just to keep it simple, we'll call it that. Now, you know something's going to happen. These are mutually exclusive and exhaustive, so either an accident or a not accident. So that probability plus that probability equals 1. If the accident happens and we end up in that state of nature, that world, then the accident's going to cost you money. You're going to lose that much. The book calls these contingent states, an event that is not certain. You know, maybe you'll have the accident, maybe you won't. Maybe the coin comes up heads, maybe tails, based on some random event. But still, contingent states, they're just commodities. It's no different from apples and oranges. My preferred assortment is 5 apples and 4 oranges. You have preferences as well about states of the world with a probabilistic outcome. I would rather have $50 with no accident and $40 if I have an accident. I like that combination of things better than, for example, $100 with no accident and $0 if there is an accident. And where's the mouse? Here we go. Okay. So here's an example of that. Your consumption, if there's an accident, is $17. Consumption with no accident is $20. Implicitly, this means if there's an accident, you lose $3. So you're at this point, 20, 17. Same as if you decided, well, I have 20 apples and 17 oranges. Same thing. Now, here, this is a condition imposed on you. You have 20 bucks. That's, the universe decided you have 20 bucks today, that's it. If there's no accident, you keep the 20. If there is an accident, you lose 3, so you end up at 17. There's nothing you can do to change this. Or is there? What if you were willing to give up some of the money you would have in the no accident condition in exchange for getting more money in the accident condition. Maybe you would rather be down there. You have preferences? Who am I to say that's wrong? How would you do that? How would you trade consumption in one state of the world that may or may not happen for consumption in a different state of the world that may or may not happen? Insurance. Okay. With no insurance, this is what you're stuck with and you can't change it. If you're in the state of the world, the second one, with no accident, you have, well, how much ever money you had, your income, M. If you end up in the other state of the world where there is an accident, you end up with your income minus whatever you lost in the accident. So you can think of this as your endowment. No accident, you have M consumption, accident, M minus L consumption. But you can shift that point around, just like in the case of non-contingent commodities, apples and oranges. You have this many apples, that many oranges. You can give up some of one to get more of the other at a particular rate, depending on the prices, to get to a different bundle, still affordable, that you like better. You can do the same thing with insurance. Now, a little terminology. If we say you buy K dollars of insurance, what that means is, if you have an accident, you get a check for K dollars. It's like when we talk about, I have $1 million of life insurance. That's not what you pay for it. That million is, well, if you die, your family gets a check for $1 million. So $K is the amount you get, the check that you get, if the accident happens. Now, how much does buying K dollars of insurance cost you? Well, the more insurance you buy, the more it costs. So you can think of the premium, the amount you have to pay to buy this insurance, as some fraction of K. Let's say it's 10%, whatever. Well, that means if you buy $1 million worth of insurance, your premium would be 0.1 times a million, $100,000. Well, whatever that fraction is that coefficient. That is a lowercase gamma. So let's say your gamma is 0.05. Well, you want to buy $100 worth of insurance. It would cost you 0.05 times 100. It would cost you $5 premium. So if there's no accident, let's say you buy insurance of some amount. You buy K dollars of coverage. If it turns out there's no accident, then you're going to end up with how much money you started with minus gamma, the premium rate, times K, the amount of insurance you bought. Your income minus the insurance premium you paid, and you get nothing for it. But if there is an accident, then in this state of the world, well, some of these terms are the same. You start with the amount of money you had minus, well, the premium rate, gamma, times the amount of insurance you bought. That's the amount of the check you sent the insurance company. So far, same as before, but this is the state of the world where there is an accident. You suffered a loss. So you take that amount, whatever it was, minus how much you lost in the accident. But you bought insurance. So you get plus how much ever insurance you bought. Now, you do a little algebra, you can factor out the k's, and you get that. And if you solve for k, you get that. Why would you want to solve for k? I'll show you. You combine the state of the world with no accident and how much your consumption be then, with the state of the world when there is an accident, so your state, whoops, don't do that. All right, let me try the mouse again, where your consumption will be this. If you combine them, you get that. Now, why would you want to rearrange it into that form? This is why. Up here, this is what we just constructed in the last slide. But look at how this thing is structured. M, well, that's your income. That's an exogenous variable. It's just a number minus gamma. Well, that's the premium rate. You don't control that. That's just what the insurance company tells you. L, that's also a number. If there's an accident, that's how much you're going to lose. Nothing you can do about that. And in the bottom, 1 minus the premium rate. This whole bit here if you plug in the variables, the values, the parameters, actually, all of that collapses down to a number. Why don't we call that number, oh gosh, I don't know, B? Because why not? We can give it a name. It's just a number, like if you plugged it all in, maybe you get 12. Okay, minus, well, they're the same thing here. The coefficient on CA, that's minus gamma over 1 minus gamma. That also evaluates to just a number. I'm going to use, okay, I'm going to use M again, because everybody does. But I want to emphasize, this is not, you know what, I can't even do that. I will pick something else. There we go. R, we haven't used R. Times CA, CNA. Well, CA is on the horizontal axis. Often, you know, when you were first learning about graphing, you'd always call that X. And the vertical axis, you'd always call Y. Nothing special about those variable names, but they're familiar. So you know what? I'm going to rename them. I'm going to call them X and Y. Changing the name of a variable doesn't change its value, doesn't change the math. I don't like calling that CA, and I don't like CNA, and I don't like calling that CA. So from now on, I'm going to call that X. I'm going to call that Y, which makes this. Does that look at all familiar to you? Y equals a constant minus some constant times X. My friends, that is the formula for a line. Y equals mx plus b, remember that? It's just the formula for a line. That's the vertical, that's the horizontal, that's the vertical intercept, and that's the slope. In this case, it's negative because the line is going down to the right. Don't lock up on me. Okay, this is the state of the world, no accident, intersect. The top left. About there. This, including the minus sign, is the slope of this line. And that is state of the world with accident. So this bit, it's just the formula of this line. Why do you want the formula of that line? Because just like before, to solve for the optimum consumption bundle, you need to find the point where the slope of the indifference curve, representing your preferences, is the same as the slope of the budget line. What does the budget line mean when you're dealing with contingent commodities, different states of the world? It means exactly the same thing it did 2 chapters ago, 3 chapters ago. It is the rate at which you can exchange one thing for the other. Instead of having that many apples and that many oranges and preferring where these are tangent, let's see if I can make, there we go. Instead of having this many apples and this many oranges here, but really preferring that many apples and that many oranges, all you're doing, and you can trade apples and oranges at the ratio of their prices. Here, you can trade off consumption in the state of the world where there's no accident for consumption in the state of the world where there is an accident. You could be here. If there's no accident, I'll have less money. But if there is an accident, I'll have more money by buying insurance. And the rate you can exchange consumption in these 2 states of the world is a function, a very simple function, of the premium rate. Now, preferences. What does it mean to have preferences over uncertain future events? Well, you know you want the outcome with the most money, the most consumption, but given that you're not certain which one you're going to end up in, you're going to have opinions about the probabilities, and you're going to form a utility function we call expected utility. It's one name for it, which is, well, if, let's say it's, you're sure that it's going to be a 50-50 outcome, flip of a fair coin, and you believe if it comes up this way, you'll get $90, that way you get nothing, and there's an equal chance of both of them happening. Well, what is your utility over this consumption bundle of these 2 uncertain states of the world? It is, well, if you win, you'll get some utility from $90, depending on your utility function. If you lose, well, you'll end up with $0. That gives you some level of utility. Again, you just plug it into the utility function. And you discount each by the probability of that outcome happening. Now, if your utility function is such that $90 gives you 12 happiness units, $0 gives you 2 happiness units, well, then your expected utility, your utility, in a sense, over this combination of uncertain futures is 0.5 times the utility in that outcome plus 0.5, 50% chance of the utility in that outcome. 1/2 times 12 plus 1/2 times 2. Your expected utility over this combination of uncertain outcomes is 7. All you do is you take the outcome in the one state of the world. I'll end up with $90, 100 apples, whatever. Plug that into your utility function. How happy would that outcome make you? Then you do the same with the other outcome. Plug that into the utility function and see how happy that outcome would make you. And then you weight them based on the probability of each outcome happening. In this case, 50-50. Let's see here. What all this boils down to is, usually for most people, utility is not linear in money. What this means is, if I double the amount of money you have, it will not double the amount of utility you have. It'll increase your utility, but not by double. Your first $1 million makes you really happy. Your second $1 million makes you happier, but not, the increase isn't as big as from the first million. It maybe increases your happiness another 30%. So, just like with consumption bundles, where because nicely behaved indifference curves, when we're dealing with apples and oranges, people tend to prefer intermediate amounts. If here's your budget line, well, all oranges or all apples don't make people as happy, usually, as a mixture. People like intermediate amounts. By having some apples and some oranges, you can get to a higher indifference curve. You can be happier. The same is true of consumption in different states of the world. If this is consumption where there's an accident, and this is consumption where there's no accident, well, look at this point up here. This is a state of the world where if there's no accident, you've got a ton of money. But if there is an accident, you have nothing. Well, if the average of, let's say, no accident, you have $1 million. Accident, you have nothing. Are you indifferent between that and the average of the two? The case where if there's an accident, you have $500,000. Excuse me, if there's no accident, you have $500,000. If there is an accident, you have $500,000. I don't know about you, but I would much rather have a guaranteed $500,000 in no matter what state of the world. I'd rather have that than the extreme of either $1 million or nothing. Here's another example. I have a coin. I'll flip it. You have a choice. You can either have $500 million guaranteed, period, end of story. Or you can have a 50-50 gamble. Between, if it comes up heads, you get $1 billion. Tails, nothing. Everybody's going to pick everybody who's not nuts, is going to pick, I'd rather have $500 million guaranteed. Well, what if I said, all right, the expected value of those is equal. If you flip the coin an infinite number of times, you'd end up with, on average, $500 million. Would you rather have $500 million guaranteed or a 50-50 chance of $2 billion? Well, the expected value of that gamble, half of $2 billion, is $1 billion. I'd still rather have the guaranteed $500 million because I have declining marginal utility of money. Money, utility. It goes like that. Well, written very badly. That's close enough. As you get more money, you do get happier. But as you get more and more and more money, the curve starts to flatten out until you get to the point where a whole bunch more money only makes you a tiny bit happier. Bill Gates, give him another $1 billion. Is he going to throw a party? No. Let's see, next. Oh, here it is graphically, what I just described to you. Okay, so if you want to find out, let's see. Okay, this looks just like something from 2-3 chapters ago, except now it's consumption in this state of the world, consumption of that state of the world. This is the bundle that they start with. You can choose to buy insurance, moving this way. So you end up with, because you're paying for the insurance, paying the premium, less money if there's no accident, but more money if there is an accident. The rate, the slope of the indifference curve, is the premium rate divided by 1 minus the premium rate. Now, and you have preferences over these two states of the world. Here, that is the highest indifference curve you can get to. So that if there's no accident, you have that much consumption. If there is an accident, you have that much. Going from here to any point southeast of it, you're buying insurance, right? But what about this part? Well, if there's no accident, you only have this much consumption. How do you end up with a point up here? It's the same thing, except this way, you're not buying insurance, you're selling insurance. I want to be up here. This means, all right, you give me money. If there's no accident, I keep it. My consumption is higher. But if there is an accident, not only do I lose money from the accident, but I also give you a check. If you start here, this is buying insurance. This is selling insurance. So, if somebody's facing an insurance opportunity, a gamble of any kind, all you have to do to find how much insurance would make this person happiest, the optimal consumption bundle of contingent commodities, is the point where the indifference curve is tangent to the budget line. Well, you find the slope of the indifference curve, same way as before. It's equal to the marginal rate of substitution, which in turn is the marginal utility of this thing divided by the marginal utility of that thing, which is the partial derivative of the function. The slope of the budget constraint, that's, if it's an insurance premium, 1 minus, it's this thing. And you have the budget constraint. Here, notice there's a difference. The marginal utility, this is the slope of the indifference curve, the marginal rate of substitution. It's the marginal utility of this thing, the partial derivative of the utility function with respect to this variable, divided by the partial derivative of the utility function with respect to this variable, multiplied by the probabilities. You think there's a pi probability of this state of the world happening, and this other probability of this state of the world happening. This probability of an accident, this probability of not accident, which you could also rewrite this as 1 minus pi a, because they have to add up to 1. Let's see. Is there anything else here tremendously interesting? You know what? That's the only concept really of this chapter. It is this. You find the preferred consumption bundle between contingent consumption, the same way as you did with apples and oranges. We just call them different things. This is CA, not X1. This is CNA, not X2. Other than that, the same analysis principles work. I will show you a worked out example in the next video. Thank you for watching.